Right, everybody, we are live. You can start in 5, 4. You're on mute. Start over.
Hello, everyone. This is our Ask the Expert session. So we have today Dr. Alexandra Okada, a senior researcher at the Faculty of Wellbeing, Education and Language Studies. She's visiting associate professor in Brazil and Portugal. And her research focuses on responsible research and innovation, open science, living labs, and education for sustainability. Ali is the principal investigator of Connect Open Schooling with future-oriented science, and that will be the objective or the focus of her presentation today. Next, so as you can see, we have Professor Chris Batt. So he's professor of applied mathematics at the University of Bath. He has worked closely with the Met Office on the development of models for weather and climate forecasting. Chris received his PhD in applied mathematics and scientific computing from the University of Oxford. And he's got other research interests like wide aspects of industrial mathematics. Most recently, Chris has been working on the application of deep learning to environmental problems. He is Director of Knowledge Exchange at the Institute of Mathematical Innovation. He is a former co-director of the Climate Network for the Mathematics and Climate, and he will also introduce this group to us today. Next, so we have Ian Kenny. So Ian is currently a visiting fellow at the Open University, with research interest in complexity theory, misinformation, climate change modeling, and computational theory. And Ian received his PhD in swarm computation from the Open University. And finally, this is me. So Dee Hackbeyer, so I am senior lecturer in computing and communications. I received my Master of Engineering and PhD from Télécom Bretagne in Brest, France. My research interests include signal processing applied to communications and oceanography, channel coding, digital communications and information theory, misinformation, and climate change. And this is all of us today for the session Ask the Expert, and welcome everyone on board. So the agenda for today, it's not rigid, of course, because we will have your questions coming live. So I will just start by talking about my research interest in time series analysis applied to environmental data and why we do climate change modeling, why it is important to do forecasts and predictions. And then Chris will follow up in the field of developing model for weather and climate forecasting, and he will talk about the research in the climate network. Then we have Ali. She will introduce her Connect collaborative platform, and she will discuss how this platform connects science professionals and facilitates partnership interactions. And then Ian will come back to talk about the project that we are currently working on in climate modeling, which is the Rapid Adaptive Climate Change Model Discovery. And then, of course, we will conclude the session. So as I said, we will have your questions coming live, so feel free to ask the questions. We are here for that. So I will share my screen, and then you will see my slides. So I will put my slides. I will just keep this on the side, and I think I won't be able to see the chat, Katrina, if I go on the full mode. So I will check this, the chat from time to time, yeah? So in my teaser, I was saying, I was talking about climate change and how we are responsible for climate change. But the good news is that also we can contribute to improve it. We are doing climate change modeling. We are doing predictions and forecasts. And we are trying to overcome these problems and to detect them beforehand. So when I was working, and I'm still working on time series analysis, you will probably come across some keywords like cross-correlation, and there is new methods that people have been applying in time series analysis One of them very famous, called the empirical mode decomposition and the Hilbert-Huang transform. And these are based mainly on analyzing non-stationary time series. And instead of calculating a normal correlation coefficient, you will see advanced tools taking into account variabilities like the time-dependent intrinsic correlation. So these are some background and objectives. The recorded time series in marine sciences, for example, environmental time sciences in general, climate change time series, they are longer and longer. There is an increase in sampling frequency. I came across time series with milliseconds, nanoseconds, because it is automatic. So what we do is that we average sometimes to the minute, half an hour or an hour, depending on the variable that we are looking at. So these time series are often non-linear, non-stationary. They are multi-scale and they are very, very, very noisy. So we need some adequate and specific methods needed. And that's why the previous tools like, Fourier, usual spectral analysis will not be appropriate. So we need another tool. And what I was working on is the application of the empirical mode decomposition method. This method first emerge in finance. Usually it's not uncommon that you will find researchers pick methods that have been successful in so many other domains to apply it in a totally different domain. So this method first, when it emerged in 1998, it emerged in the finance sector a lot. And then people increasingly from the 2000s, they've been starting exploring it in the environmental time series, and it's been more and more successful. And this method can be used to analyze the time series, but also to analyze the correlations, because there is a lot of variability between the time series. So you can analyze chlorophyll, temperature, salinity, turbidity, density. This list is non-exhaustive. Rainfall, all the variables that these researchers record. So you can apply them and you can analyze them based on this method. So why we do such analysis, why we are interested in analyzing the time series? This is part of climate modeling. For example, if you look at surface tides, these are the heartbeat of the ocean, and these are controlled by relative movement of the earth. So these are deterministic. So if you take any deterministic tools, this will work. However, if you look at the internal tides, that's the problem. These are highly nonlinear signals, so they display highly nonlinear oscillations. They've got a wide spectral content, and usually we cannot predict them. Even on a short time scale, it's very difficult. If you look, for example, at the tide waves, you can predict them. That's why when I go on the sea, Norfolk or whatever, I usually look at the tides to see if I am able to book a boat trip in the morning or in the afternoon, because otherwise it won't be possible. So these are deterministic, but the internal are not. So in situ, the time series of all these variables, we look at their characteristics. We look at the characteristics of the internal tides in particular, because these will affect the way my prediction will be. They are non-predictable, so I need to explore them in details. I need new tools. I need to understand the way they propagate and the way they modify the shape of the coast of the ocean, etc. So that's why we look at the advanced spectral method, because the classical ones like Fourier, I said, for example, they are perfect when it comes to linear signals or periodic or stationary. But in earth science, it's the opposite. It's unevenly spaced. Although I want to record every minute or every 5 minutes or every half an hour, there are always issues. The sensor didn't work, there were currents, there were waves, then I've got missing data. So you can see, so it's usually unevenly spaced and non-stationary. There is a similar approach to Fourier, but that will work for missing data. It's called the Lombus-Cargill approach. But then the one that I am talking about is the EMD, is a new adaptive data science method. And this one was introduced in 1998. And then people, they move also from the time decomposition to the spectral domain by applying the Hilbert-Huang transform. So these complexity multi-scale fluctuations, the need of high frequency sampling, because if we have like, for example, every minute recording, sometimes it's useless. Ian will talk about rainfall in a particular area. It's useless to have it every minute. So sometimes from day to day, there is not big change, but every 3 days, for example, in some area. But in some others, we need really high frequency sampling to detect every fluctuations, and we need these adequate methodologies. So the stochastic variability on a large range of scales, the turbulent-like small-scale stochastic fluctuations, and the large-scale deterministic period for tidal and daily cycle, and many missing data makes that we need EMD. So what's EMD? The empirical mode decomposition, because it is still empirical, although it has been discovered in 1998. So it decomposes the signal into a sum of modes. Yeah, that's not new. Fourier does that. Yeah, but Fourier provides tens and tens of useless modes. And EMD will decompose them into a meaningful sum. It will say this is, for example, that tidal wave, that's the monthly, that's the semi-monthly, that's the annual. It will identify some deterministics, and you will be looking at the non-deterministic ones. Also, the good news, although it's empirical, these functions, they form a basis which is nearly orthogonal, and they are, the modes are nearly very localized in frequency space, and they can act like a filter bank. For example, you can do denoising of time series using the EMD. Great, good news. There have been so many papers using EMD for denoising the time series. So it can be used for detrending or denoising. Detrending is removing the trend, which means that if you look at your time series and you see that it's generally increasing or generally decreasing, what you will do is that you will remove that trend and you will explore only, I will love that, I love the core of your time series, what's really affecting your variability. This method can be applied to nonlinear and non-stationary data. The good news also, which is something that I am looking at currently with Ian in our project, if we have a very small number of data points, we want to predict the climate change, even with a small number of data points, and good news, EMD can do that. So it's not something that is totally working on its own, but it can complement the previous old tools like Fourier or wavelets. This paper that has been published in 1998, currently there is nearly 26,000 citations for these papers, and there is hundreds of papers applying these new methods to always new fields, in medicines, in finance, in climate change currently, signal processing, mechanical engineering, earthquakes, biomedical studies. Once I was delivering training in Washington, and there was a lady participating. She came with a very, very odd time series to me. She said that she is looking at carrots growth, and she came with time series of her carrot growth, and we were able to use EMD for her carrot growth to predict how her carrots or these different variations of her carrot will evolve and which one will grow big. Amazing. But it's empirical because still not exact mathematical reasons for that. Okay, so I will be going quickly here through a demo. So EMD is the process when you have a signal, you take the maximum and the minimum, and then you average, you interpole in between, you remove it to the previous time series, you get a residual. If you still have variation, you carry on. When do you stop? When you don't have any variation or you have something that is or monotonic, increasing or decreasing monotonically. So then you stop, and that will be called the residue. So it starts like that. So if you get a first iteration, you pick the maximum, you interpole, you do an interpolation, you pick the minimum, and then you take an average. The average of that, you remove it to your original data, and you get what we call a residue. As long as you have variations in the residue, which is the case, you carry on. You iterate the process, yeah? So you iterate the process until no variations anymore. So now I have removed all the variation, and it is periodic, totally deterministic. That would be one mode in the EMD. And what I will be doing now, reiterating on mode 2, mode 3, mode 4, until I try to reconstruct all my signal. So how many modes? Very, very good questions. How many modes can I have? Unlike Fourier, the EMD can provide a maximum of log in base 2 of n. N is the number of samples. Just to give you an idea, I have analyzed a time series with 100,000 samples, and the maximum number of IMF you can get was 12 to 13, which is amazing. So if you have to analyze this with Fourier, you can get 90 or 100 modes. You will be lost in which one is important and which one is providing the variations and which one you need to focus on for predictions. Among the 12 modes or 13 modes that I have received for my 100,000 samples, there will be so many deterministic tidal waves, and there might be 3 to 4 non-deterministic that you will focus on. So it gives you very, very good start to do your forecast and your prediction. And finally, what you can do with EMD is to correlate time series and to correlate variable. What people do now is that they just compute the correlation with one coefficient. But as you can see, that's not really representative, and that's not really correct, because sometimes time series might be very correlated. In October, let's say in the Rainian Islet in the hemisphere south, when I was working on some time series, there will be a strong correlation between the wind and the sea temperature. However, if you go to other period, there will be very, very low correlations, because they've got their winter season and their summer season. So although you might have a global correlation coefficient, so usually it's between 0 and 1, let's say 0.5, it doesn't mean that your time series are half correlated. So we need other tools like the TDIC, the time-dependent intrinsic correlation. It will give you all the patterns. Here is a high one, here is a low correlation, and this is opposite way, and this is the same way. So one increases, the other increases, it will be positive, and one variable increases, the other decreases, it will be negative. So that's what I call the problem of nonsense correlation. If I use the wavelet transform, or the mother wavelet will depend on the type of data. However, if I use the spectral analysis after EMD, there is no predefined basis function or mother wavelet. So that's why we use the time-dependent structure to decompose the signal using EMD. We use, remember I said the modes are very localized in frequency. So you can compute a local frequency, so you can compute an instantaneous period. And then you can determine an adaptive window. You will slide this window, you will slide this window, and you will compute the time-dependent intrinsic coefficients. So how it will look like? So if you have a global correlation coefficient, let's say an example that I picked, minus 0.35. If I compute the global one, the usual one, so it tells me that it is negative. So temperature and chlorophyll are, when one increases, the other decreases, but it's very low. The reality is totally different from that. So that's the global one. So if I use the EMD and the TDIC, look what I obtain. All this. So here I have a time series that was analyzed between August and April from one year to the other one. And the global correlation coefficient is simply the peak of your triangle. That's my minus 0.35. But what happens in between? Lots of things. You can see that in periods of March and April, I was reaching high positive correlation due to the blue between the chlorophyll and the temperature. You have temperatures increasing and there is a bloom, so the chlorophyll also increases. And here I can go to high correlation, going to 0.6 instead of my minus 0.33. And if you look at the periods of, early autumn, so this was in the Raelian Island. So you can see here in September and October, we've got negative because you go to blue, but going to minus 0.9. So very, very highly correlated. When one increases, the other decreases. This cannot be seen with the usual classic tools of global correlation, but it can be used after empirical mode decomposition and after time-dependent intrinsic correlation. So when we have the lower frequency modes, sometimes we have higher correlation. And when we compute these modes after the empirical mode decomposition, the last one, the residue, is the trend. So if when you read papers about detrending or denoising, usually they do EMD, they get the residual, which is the last mode, and they subtract it to their time series, and that gives the trend. When we look at time series, we will mostly find highly correlated trends, but then we will look at all the other modes, the deterministic and the non-deterministic modes. Sometimes we have very small correlation, and this might be due to what we call the mode mixing, which is a mixing of some different modes in the same scale. But there are methods that have been looking at variations of EMD and how to separate the same mode in different scales. Yeah, so just to keep in mind, people, we are doing forecasts, we are doing predictions, we look at climate change. These environmental time series, they are often very noisy, very complex, and strongly non-stationary. Very few frequency decomposition methods are adapted to analyze such series. And that's why we use EMD, the empirical mode decomposition, and we apply the Hilbert-Huang spectral analysis as adaptive methods. There were so many observations from so many time series that I have analyzed. The ones that I presented last were from the Gascoyne Inlet in Canada. And the application of EMD will provide a group of tidal waves detected. And the non-tidals are very important. So you can also analyze and explore and investigate these non-stationary correlations. If you want to correlate different variables, the best thing to do is not the global correlation coefficients, but remember that sliding window and that triangle, that's the time-dependent intrinsic correlation, where you display different patterns of correlations at different scales. And in other studies I've been working on, I was comparing the EMD with wavelets and with some other cross correlations. So this is what you need to keep in mind, all the complexity of the time series. Chris will follow up, Ali and Ian later. The fluctuations over a large range. We have time series from seconds to thousands of years. We need adequate methods. We have the methodology presented. These are general and can be applied to face challenges. And remember now these keywords that I have at the beginning. So I hope that you got now some of these: cross correlation, the empirical mode decomposition, the spectral analysis, Hilbert-Huang transform, stationarity and non-stationarity, time-dependent intrinsic correlations, and time series. Thank you very much. So let's see if we have any questions. I don't think, Katrina, that I had questions on the go, but if there are any questions, I'm more than happy to look at that, because otherwise, so yeah, okay. So Chris, would you like to follow up with your experience in the field of developing methods for models for weather and climate forecasting? And Chris, also, we talk about research in climate network. The floor is over to you, Chris.
Thank you, Duha. Well, I shall talk a little bit about how maths goes about predicting the climate. And you might wonder, why am I a mathematician talking about this rather than a meteorologist or climate expert? But actually, mathematics is really, really important in predicting the climate. So we've already heard a bit from Duha about time series and how she uses these really clever methods to analyze them. And we need time series to understand that our climate really is changing and is changing rapidly. So where do we get time series from? Well, here are the sort of various things that the Met Office use, and they've been using these for about 150 years or so to collect information both on weather and on climate, with most of the information nowadays coming from satellites, but there's all sorts of other sources that we can use to see what's going on. And if you do measurements, you find that our climate really is changing, and it is changing rather fast. So here is a really important measurement. This is the measurement of the mean temperature of the Earth since the formation of the Met Office in 1850. And in that time, the mean temperature has gone up by about 1.5 degrees Celsius. You can see this is a classic time series in the sense that you've got a lot of random variation with the temperature going up and down, but there is a very, very clear trend. And since 1940, the mean temperature in the Earth has basically gone up pretty well monotonically. So that's pretty clear. Well, there we go. Here's another measurement. You can send satellites up above the Arctic, and you can measure the amount of ice. And this is a NASA satellite that's measured the amount of ice over the last 50 or so years. And in that time, we have lost a very significant amount of the Arctic ice. And if we carry on the rate we're going, we'll have lost it all by the end of this century. Here's another time series. This is time series of the mean ocean, height of the ocean, mean sea level. From a time series point of view, this is quite boring. It's absolutely dead linear. But what it's showing us is that the ocean is going up by about 3.5 millimeters per year. This is mainly because it's warming, and as water warms, it expands and that goes up. So these three are time series which very clearly show that the Earth's climate has been changing since the foundation of the Met Office about 150 years ago. But climate isn't just what's happened in the last 150 years. Climate is what happens over many thousands, indeed millions of years. And climate has changed a lot in the past, but it changes, if left to itself, rather more slowly. How do we know this? We can't go back, obviously, and take measurements with satellites or something, but there are a number of ways of seeing what the climate has done in the past. One is looking at old records. So, for example, measurements of the weather have been going on since Roman times. You can look at pollen, which tells you a very good indication of what some ancient pollen tells you, very good indication of what the temperatures were. Tree rings, again, a very good indicator. But perhaps the best of all is to go to the Arctic or the Antarctic and drill down into the ice. And when you drill down into the ice, you can see layers of ice year on year, and each layer has oxygen in it. And by measuring the amount of the oxygen 18 isotope, you can actually exactly work out what the temperature was. This is one of my favorite graphs ever. This is a graph of the Earth's temperature over the last 500,000 years. The top curve, which is the blue curve, is the temperature measured from a European ice core, Epica. And you can see that the temperature goes up and down and up and down and up and down and up and down. And the period for going up and down is about 100,000 years. The green curve is temperature measurement taken from Vostok, which is a Russian ice core, showing virtually the same amount of going up and down. On the bottom is a red curve showing the total amount of ice in the Earth. It's inverted, so the high amounts of ice are lower than the low amounts. And so you can see that high amounts of ice correlate to low temperatures and low amounts of ice to high temperatures. And this is the ice ages, and the ice ages have a period of about 100,000 years, and we are currently in the warm period after the last ice age, which finished about 10,000 years ago. One of the things about climate change is people say, well, why should we be worried about the climate? It's always changing. And the answer is yes, but if you leave it to itself, it takes about 100,000 years. And current climate change is much faster. This is a more recent set of measurements of the temperature, again, mostly using ice cores, but also with tree rings and so on. So we've got different curves for the different ways of measuring the temperature. And in the last 2,000 years, the Earth gradually warmed up to what's called the medieval warm period. And then it cooled down into the little ice age, and that was due to the sun cooling down. And then we get to about 1850 or so, when the Met Office was founded and the Industrial Revolution started, and that's what the temperature has done since. It's gone very sharply up, and this is called a hockey stick. One of the other indicators of climate change is to look at the amount of carbon dioxide in the atmosphere. And again, you can measure this from ice cores. And over the last 500,000 years, it's been going up and down and up and down and up and down, with a sort of mean value of around about, well, I suppose mean value of about 250 parts per million, maximum 270. But since recent measurements have been made, it's gone like that. The amount of carbon dioxide in the atmosphere has more or less doubled. And here are measurements taken at the Mauna Loa. This is called the Keeling curve of carbon dioxide, showing a great rise in the amount of carbon dioxide in the atmosphere with seasonal variation, but a very strong trend, taking us up to now 420 parts per million. So that's data. So we can gather lots of data and we can analyze it the ways that Duha explained. But data on its own is it's a dangerous thing, because it's difficult to know what's going on. So in terms of climate change, we're seeing rises in temperature and we've seen rises in carbon dioxide. And there are two possibilities. One is, well, three possibilities. One is that temperature rises cause an increase in carbon dioxide. So that's a kind of natural variation. The alternative is that rises in carbon dioxide cause a rise in temperature. That's what we're worried about. That's what we call anthropogenic climate change. Or it could be that temperature and carbon dioxide are completely independent and not related to each other. And this is where we need mathematical models to be able to make sense of the data. And here's a picture which appeared in the recent IPCC report. And this is the predictions of two mathematical models of the climate from 1850, when the Met Office was founded. The red curve is the prediction that you get if you put in the human effects of adding carbon dioxide to the atmosphere, plus what we call natural drivers, which are things like El Nino and volcanoes and variations in the sun. The blue curve is what happens if you don't include the carbon dioxide that humans have added. And so those are the two models running, and the sort of fudgy bit shows the uncertainty in those models. And you can see that the red curve lies pretty close to the actual observed temperatures, and the blue curve lies nowhere near. And this is very, very revealing, because what the model is showing is that there's a direct causal link between carbon dioxide and temperature rise, and also that the model is predicting what you see. So this validates our model. So that's really important. And once you've validated the model against the data and seen what's going on, you can then go into the future. And here are various predictions that are made into the future. So by the year 2100, we're predicting between a 2-degree and a 5-degree rise, depending upon which climate center you go along with. The Japanese predict 5 degrees, the Americans 2 degrees, and the Brits halfway in the middle. And the reason there are different predictions is that you make different predictions depending upon what these are what's called represented climate predictions. for different levels of human activity. So the Americans might assume that, well, essentially it depends upon your assumptions on how much CO2 you're pumping into the atmosphere for different things, but all of them are predicting a significant temperature rise. So that's what models do. So what is a model? Well, a climate model is a mathematical and computer simulation of the climate. And all models start from the laws of physics. Modern modeling using deep learning, which is what I do, takes the laws of physics, but throws in a huge amount of data as well to build the model from. So the models are then informed by data and they are tested against data. And once you've got a model, then that's what you can use to predict the future climate. And this is basically what I do. And that's what the Met Office does and what the Hadley Centre and all these outfits do.
Chris, we have a question, Chris.
Yes.
Is climate change and the increase in temperature reversible, or can we only slow it down?
That's extremely good question. It's reversible if we suck large amounts of carbon dioxide out of the atmosphere. So we can change things, but we have to act very positively to do it. So let's carry on with the model and explain, and because the model actually helps us work out what we have to do. So what you do in a model is you take all the things that you think make up the climate. So the climate is basically the Earth's weather, which is the speed of the wind, the temperature, the density, the moisture. You add into that things like the effect of the sun, mountains, vegetation, and you throw the whole thing into this ghastly set of equations, which are what we call the Navier-Stokes equations. And then you try to solve that set of equations, and solving that set of equations allows you to predict both the weather in the short term and the climate in the long term. So to help answer your question, how might we know what we have to do? Well, we can feed into these equations the amount of carbon dioxide in the atmosphere, and that tells us what's likely to happen depending upon the amount of carbon dioxide. So this is what we do. These equations are extremely hard to solve. They're basically beyond the limits of any human to solve. So what you do is you discretize them. So you divide the Earth up into lots of little cubes. You solve the equation on each cube, and then you kind of build up the climate prediction by putting all those cubes together. And complex models of the climate nowadays have billions of unknowns and billions of these cubes. And that's how these predictions are made. And that's what leads to these kind of what we call complex global circulation models, which are currently used by the IPCC to inform what's going to happen in the future and what could happen in the future with various interventions, such as sucking carbon dioxide out of the atmosphere. It's not all doom and gloom. We can change it, but we have to do a lot of effort to do that. So let me tell you very briefly about ClimathNet, which is this organization that we put together to do development of these sort of models. So ClimathNet stands for Climate Mathematics Network, which is a group of mathematicians from many universities in the UK that works with the Met Office, the Hadley Centre, European Centre for Medium Range Weather Forecasting, and other climate groups to do various things. So one is that we develop advanced climate models, these general circulation models, to do these sort of big predictions. The sort of work I'm mostly involved with is developing numerical methods to solve these, and also now using deep learning to try to speed these things up. A climate model on its own isn't particularly useful to a human being. What we also need to do is understand the impact of climate change. So we take these models and apply them to other things to see what the impact is. And another thing that I'm very involved is what we call developing reduced climate models, which are simplifications of these models, which allow you to make longer term predictions. And these are the things we use, things like ice age modeling, looking at El Nino, looking at the behavior of the Atlantic, and tipping points. And tipping points exactly answers your question. A tipping point is, are we past the point of no return, or can we do something about it? And my answer to that is quite definitively, we are not past the point of no return. We can do something about it, but we've got to get on and do it. And finally, ClimathNet is also very much involved in outreach, going out to schools and talking about climate modelling. One of the things I do with schools is talk about a simplified model of the climate called an energy balance model, where you try to look at the climate by balancing the amount of energy you get from the sun by the amount of energy that the Earth radiates into space and various feedback loops that occur within the Earth. And this is a simplified climate model, which is actually quite predictive. And the nice thing about this model is that you can code it up in Python onto quite a small machine. And this is the demo package we take around schools. And the thing bottom right is the Raspberry Pi that has this climate model built into it. There's the screen, and here's a teddy bear to make it all look a bit more friendly. And if you want, this is Tina, one of my PhD students, who is really good at explaining climate change to anyone that wants to hear. So that's one thing we do, is outreach. This is the sort of work, this is modeling the ice ages. As I say, the bottom picture are the pictures of the temperature going up and down in the ice ages. And the top is a model that we've developed for this called the PPO4 model, which I believe actually does give very good predictions of the ice ages. And that allows us to predict into the future as well. And finally, we work, I'd say, on the impact of climate change, looking at the impact of climate on things like the agriculture, health, energy, and so on. And this guy top right, who is our kind of pin-up model, is Tozin. And he does amazing work looking at the impact of climate change on agriculture. And in particular, he's standing in front of a whole ton of cocoa trees. He's looking at the impact of climate change on cocoa farming in Nigeria. And that's really, really interesting and important stuff. So just to finish, the conclusion is that the time series analysis shows us a lot of evidence for climate change, but we have to be careful how we interpret it. And that's why we need models to help us understand the data. And I would argue that mathematically based climate models are our best way of predicting the future and working out what to do next. So thank you very much.
Thank you very much, Chris. I think, Katrina, yeah, there is no other questions that I can see. So Ali will introduce her Connect collaborative platform. Ali will discuss how this platform connects science professionals and facilitates partnership interactions. The floor is over to you.
Hello, everyone. So it's a great pleasure to be here. So we just heard from Dura and Chris that climate models are essential to understand how climate is changing in the past, how it's changing now, and to predict the future. But we cannot do this alone. Scientists must cooperate with each other. So Connect platform was developed to engage all actors in society to promote open science and open schooling. So here you can see that we are trying to engage educators, learners, scientists, consultants, mentors, and policymakers. And it's a multi-actor, multi-language platform for collaborative learning, knowledge exchange, participatory research groups. And I would like to show here that we are trying to bring all these functionalities, yes, that is available for platforms, resources, social network, database, analytics engine, user management, and the content management systems to create this interface, yes, to support climate experts. So I'm going to show this is not only one topic in the platform. We are working with all, global challenges. But if we go to the platform and we wanted to see events related to climate, like this one now, so searching, you can see there are two events. This one, Ask the Expert, and Connect the Student online conference, when students are discussing about climate. And if you wanted to search you know, scientists and the experts on climate, you can go to members and you see Duha, Ian, probably Chris will join us as well. And you can see their profiles, which is amazing. You can see that the scientists work with this interdisciplinary approach. We have social scientists, computer scientists, we have geologists, people interested in policy, like climate governance. So all this variety is so important to discuss climate models. And also in this platform offers resources for all levels of education, from primary, secondary, and higher education, in particular, teachers' professional development. Because we needed to explain and to create opportunities for this generation and the next generations to develop the competencies that, like Chris, Duha, Yan, they have, yes, as a scientists. For instance, you have here resources on microplastics. By the way, there is scientific papers that make some links between microplastics and the climate models, the climate change, and the carbon neutral. So lots of resources that are related to climate to understand better these concepts, and the discussions in all these different languages. So you can see 600 members, 40 discussions, and 5 discussions related to the tags related to climate, lots of documents that scientists and the whole community, they can share. And also we have groups, and the groups with some tools for self-assessment, and also working together to present their studies in conferences. So there is this next conference, which is about the global education and the green economy, that we will be discussing this topic, climate models. So analytics, which is very important to understand how the groups and the community are active in the platform. So basically, we have here, yes, you can see this cooperation between University of Bath and with Chris and the Durham Open University in the UK. So there are lots of cooperations across the world, yes, and in Connect, working with the climate. And you can see like in Romania, in Greece, and in Brazil. So we would like to just to say thank you for this opportunity. We have Exus, which is AI company producing that platform, and 10 partners, yes. So it was a great opportunity here, and open for questions and discussion. Thank you.
Thank you very much, Ali, for this interesting presentation as well. So just Ian now, he will come back to talk about the project we are currently working on, and we will conclude the session with this last presentation. So the rapid adaptive climate change model discovery. And so I will share your slides, Ian, yeah?
Yes, please. Just bear with me for 2 seconds.
Yeah. Are you set up, Ian?
Hang on, sorry about this.
No, that's fine.
Just bear with me a minute. I can't get my notes on screen, so if somebody can fill in time there.
Yeah, so that's the rapid adaptive climate change model that Ian will be talking about. So what the 2 graphs here show are some previous work by Sevelek, where he was looking at some time series and he was able to predict the weather forecast the last 5 years. So it was between 2018 and 2022. And he was introducing a new approach to climate forecasting. Maybe, Ian, you can use the slides, that's fine.
Yeah, what we're trying to do here is use a different approach to the one Chris previously talked about, to try and provide a more responsive model, which allows localized predictions to be made, which adapt to the more rapidly adapting climate. This is based on a publication in 2018 that was able to predict that the subsequent 4 years from 2018 to 2022 was going to be much warmer than the previous average. So if we can go to the next slide, please.
Yeah.
So what we are aiming to do with this project is to find a mathematical tracker, which is basically trying to find the probabilistic distribution within the mathematical model that enables the time series that Duha talked about to be collected together within a single mathematical model, which effectively joins together the relationships which Duha's model brings out. So what we do is find the results of Duha's model and then iterate that model so it finds the connections between those models, and if you like, moves the system state, which it then represents, into the next state, which is the climate state, which it subsequently predicts. This has the advantage of learning the characteristics of the data set as it is now. So what we are effectively doing is measuring the difference between what our model says it should be now and what we are actually observing in our data set moving forward. And by doing that, we can make the model more responsive on a localized data set. If you move to the next slide, please. Yeah. So this is a schematic of the model as it is currently intended to be. What we have is what I've referred to, which is an iterated function system. This is the series of functions which predict where the system is going to move with probabilistic values. So each function within this system is applied probabilistically to the current state of the system in order to produce a prediction of the system going forward. So the aim will be to compare the model between itself and others. And then
I have a question, Ian. So we have a question. If climate change in future causes serious problems, are there any defense systems developed?
That is a very interesting question.
Policy making questions.
As we go through this slide, so the reason we're trying to do this is to provide a more responsive approach for public policy making. So the going forward, what we're intending to do is provide a model which is able to produce the localized modeling, which enables public policy to make changes based on the localized predictions. If we move on to the next, I think is the next slide.
What's the relevance? This is what we talk about it.
This is what we're talking about. So to give you an example, the reason that we would want to do this is to allow localized climate changes to be recognized by public policymakers so that subsequent sustainability models can be used to inform what we can do to mitigate the effects of significant climate change. So what that might be is to introduce additional health support for vulnerable groups of people, the elderly, for example, ahead of time, because that's what we might be able to say is in 2 to 3 years' time, the temperature is going to be significantly hotter in a local urban environment than it is currently. And the idea of this model is to allow policymakers to make changes to avoid catastrophic health outcomes for the population. Yes, so
Yeah.
thank you very much. That's my presentation. Any questions?
Thank you very much, everyone. Yeah, thank you. I think Ali would like to share something. Maybe we have a question. Just a second. Nothing further. Yeah, so Ali, maybe you want to share, if you can unmute yourself and then we can hear you. So she wants to share something with the participants so we can get from you the outcome of this session or the presentation. I hope you have enjoyed. Thank you, Chris. Thank you, Ali, and thank you, Ian, for your presentations.
Yes. So we invite everyone, including the speakers, to get your mobile phone, add this URL, www.menti.com, and include this number, this code, 27724735, okay? Yeah. And include the 3 words that was very important for you, during these presentations. So we can see people adding their words, and we have this cloud, based on our input, feedback. By the way, while you are adding this, I can see, based on all the speakers' presentations, how important is this topic. Yes, you can see questions from local policymakers, and we can see the climate modeling research, how relevant it is now. So engaging people to understand how the models are, developed, used, implemented, and how we can draw recommendations based on the findings. This is really important. You can see that the map is changing, so it's great to hear from you all. And also I'd like to see if we have final questions, do have from the chat?
Yeah, so I will have a look. I think Katrina said that we don't have any further questions. And no, it was already some good question. We had already some good questions on the go. I think we had a variety of presentations to you just to conclude the session. So about time series analysis, prediction, forecast, and if we do our research on our own, it might not be valuable. That's why Connect platform is one of the important aspects that Ali has developed. When we even look for funds, we need collaborators, international collaborators, and the Ali platform facilitates these things. So maths are very important, as Chris highlighted. And you can see myself and Ian are working maths and oceanography background together. So we need different skills to do climate change. And the most challenging task is to convince the policymakers. So we need someone to help us with the to get the correct vocabulary to the policymaker to convince that although we do math, but we can contribute to climate change and we can connect professionals. I hope you enjoyed the sessions. Thank you very much for coming along and hope to see everyone on a different occasion. Don't forget to log into the Connect platform. Thank you very much.